Hello and welcome to this tutorial which will cover variable resistors used in audio amplifiers and typical types of faults and how to resolve them. When you look at the video, the first part what we're going to look at are circuit symbols, and this is really important because if you're going to undertake any form of service or repair and you're going to refer to service manuals or schematics, it's important to understand what these different types of symbols are. So as you can see here, we have two types of symbols, and what we have to do is really go back in time. And as you can see from the video here, we're going back to 1952. And back in 1952, the International Electrotechnical Commission actually defined standard resistor values and tolerances, which allowed then for mass manufacturing of electronic equipment. So what you see here is very common in terms of the types of symbols. So you may have a service manual or a schematic from an older amplifier, and what you'll see is in the middle part you can see like it's like a zigzag, and what that's representing there is a circuit which would say, for example, to be resistive. And as the current is trying to flow through the resistor, then it's coming across an obstacle, i.e. it's restricting the flow of current through there. But that may not always be the case, so you may not always see that type of symbol, and what you may well see is more so the symbol on the left hand side as shown in the video, where you have like an oblong shape, and that will be used then to show a fixed resistor. And I give a couple of examples here. So what I'm showing you here is that this could apply to a conventional through hole resistor, so two terminals on each side, and then that passes through the circuit board and then is soldered onto one side or both sides if it's a multi-layer board. But of course that symbol may also apply, and again as I'm showing here, to a surface mount type resistor. And then the middle part, and this again is a little bit confusing, and I appreciate that if you're undertaking repair work, this could be something which you look at and say, well, that's kind of different to what I'm seeing. And what I'm referring to here is a preset resistor, but sometimes we refer to preset resistors as trimmers. And the reason why we call them trimmers is that preset resistors are actually variable resistors, and we're able then to adjust the resistance value. And typically this would be used for adjustment, say, of DC offset within an amplifier, or more commonly you would see these trimmers or preset resistors being used to adjust the bias current for the output stages of the amplifier. But the correct symbol is as shown here, okay? But what you can see in some of the service manuals is that they show the variable resistance symbols where you have an arrow rather than just a line then with a flat, okay? But the correct symbol would be as you're shown here next to the preset resistor stroke trimmer. And then the next one is a very common one which you will see on the service manuals, and this is where we're referring then to a variable resistor. Now a variable resistor can also be referred to then as a potentiometer, and again you may find this is abbreviated, and people may well say, well, I need to create or to clean, for example, the volume pot, and what they're meaning there is the volume potentiometer, but they've just shortened it down to say the volume pot, the balance pot, treble or bass pot, and that's what that means there, okay? And then in terms of construction of these resistors, in the very early days, then these resistors were wire wound, so it was typically using constant and tight wire to create an electrical resistance. And then as technology changed, and of course electronic components developed, and in the development then of the transistor and what I would term as semiconductor type devices, and of course that would be also in parallel with thermionic type valves, then the resistors were manufactured then using carbon. And then as it started to evolve, then that moved then to carbon film, and then metal film, and then metal oxide as well. And you might say, well, I'm not too sure, what's kind of like the benefits of these different types of technologies. Well, in modern day amplifiers, wire wound resistors are still used, and they tend to be used in the output stages of the amplifiers because that is handling a higher current through the output stages. And the wire wound resistors may have a ceramic overall covering or coating, and that enables that resistor then to dissipate heat more effectively. With carbon resistors, again depending on how many years you've been using sort of audio equipment, carbon resistors really are not ideal in audio electronic circuits, and the reason for that is that they generate electrical noise. And I remember way back into the early 70s for myself, and I remember the first stereo which my brother bought, and this was actually a Russian made stereo by the company called Ragonda, and this was a Calypso type. When you put the amplifier on, you had quite a large sort of amount of buzzing or noise through there, and there was nothing wrong with the amplifier at all. In many cases it sort of told you the amplifier was on and was then operating. But the problem then with solid carbon resistors is that it does generate electrical noise. So then what the technology then moved on to then was to use like a carbon film, which reduced it a little bit, but not ideal. More commonly than not now, what you find is that virtually all the types of resistors which are used in audio amplifiers within the signal processing circuits are typically metal film type. So that means it has a ceramic former, and then over there is sprayed metal film, and of course depending on the composite of that metal film, that will deem what will be the resistance value of the resistor then. And then we also have metal oxide type as well. Now I said earlier, and you can see in the video, it refers to the standard really that came about in 1952. And when you look at different types of resistor types, it's not by chance. It all goes back to this original standard. So they will typically refer to the E series of resistors, and E24 series is probably the most common type, but that has changed. Okay, and the reason why that has changed is that the accuracy and the tolerance of these resistors has improved dramatically in the last probably 20 years. So E24 was the most common. So they have set resistance values within, and then in terms of tolerance, that would be have a 5% tolerance. So if we talk about a 100 ohm resistor, for example, its manufacturing tolerance can be within 5% of whatever that resistance value is. So when you think of a resistor maybe of 1000 ohms or 2000 ohms, that percentage tolerance still applies. But as we know, in some circuits 5% tolerance is unacceptable, and then what you can then do is you move then on to what we call the E96 range of resistors, and their tolerance then goes to 1%, or the E192 series, and these are high tolerance resistors. So this can range up to 0.5 all the way to 0.1% then of the range. And you might find these types of resistors are used, and we will see this a little bit later on in the video, where you have a high precision potentiometer which is used for an audiophile type amplifier, and it would not be uncommon there to find these resistance values typically of 0.1%. You can of course get resistance values even more accurate than that, and then what we refer to then is parts per million in terms of tolerance. So if anyone out there is interested to sort of look at that in more detail, you can look up high precision resistors and it will then come back, in terms of parts per million there. Okay, so first part we're just looking at the electrical symbols, and you may see these in both service manuals and on service schematics. And just remember that a preset resistor is a preset resistor, i.e. it's a trimmer. It's not a potentiometer, but its function is the same, but it's commonly used to refer to both, and I'm just sort of highlighting that for you just for clarity. Now the next part is I want to talk to you about Ohm's law, And for anyone who is involved with electronics, Ohm's law is something which you would be using pretty much every day. And the reason why I say every day, not that you're out there designing new electronic circuits, but understanding the principles of Ohm's law and how that applies to electronics will help you hugely when you're doing fault finding. And it may also help you as well if you want to develop your electronic skills and then start to design your own equipment. Now, before we sort of get into it, and I've made a note here in the video, there's two terminologies. Okay, so the first one is conventional current flow, and then there's something else which is then referred to actual current flow. And you may think, well, you know, what does that actually mean? Well, what I'm referring to when I talk about conventional current flow is really how electricity and the flow of electricity, stroke current, whatever terminology you want to use, within an electrical circuit. So I'm giving an example here of a 12-volt battery, and what I'm showing is a positive and negative terminal of the battery, and then I'm showing an arrow, and then underneath it says 20 milliamps, and then that shows current flowing then into the electrical symbol, which is a light emitting diode, and then the current flows through there and then returns back to the negative terminal of the battery. And we would say that current would flow from positive to negative, and that's what we mean when we talk about conventional current flow. But actually that is incorrect. It doesn't actually flow from positive to negative at all, and the reason for that is that current is actually negative. So it's an electron is a negatively charged, so a negatively charged electron needs to be attracted then to a anode. So when we talk about a battery, it has both an anode, a positively charged terminal, and a negatively charged terminal. So actual current flow means that the negatively charged electron will be attracted to the positively charged anode of the battery, and only then, or that is the correct way in which the current will then flow then. But I don't expect anyone out there to sort of change the terminology, you know, and say, okay, well, actual current flow is this. But it's important to understand that electrons are negatively charged, and they are attracted then to a positively charged anode, as is the example here in the battery. Now, the other thing that we need to clarify is what we refer to as current flow. All right, so if you did, say, a Google search, it would come up and it would tell you that the function of a resistor is to limit the amount of current that flows in an electrical circuit. And that is true. But there's a little bit more to it than that, okay? And what I'm referring to here is that we always require in any electrical circuit a potential difference. And you require this potential difference for current then to flow. If there is no potential difference, then there cannot be any current flow. And we use a terminology which is called EMF, or electromotive force. So again, to sort of explain this to you, if I had, for example, a battery which had two terminals, and both of those terminals were negative, so there was no anode or no positive terminal, if both terminals were negative, then there cannot be any current flow because there is no potential difference. If again both terminals were anodes, then again there is no potential difference, so no current can flow. So when we talk about electrical current and we refer to the amount of current that then flows through a series circuit, what I'll explain to you now is in reality what we are doing is we are changing the voltage level or the potential difference, which in itself then limits the amount of current that can flow. And I appreciate that that sounds a little bit complicated, but just stick with it and then we'll walk through this together. Okay, so I'm using this example here. So if you looked up the specifications for a light emitting diode, a green one, and this is available in a 5mm diameter. If you look at the data sheet, then typically the LED will draw, for example, 20 milliamps, which is a nominal current, at 2 volts. Now we know that its operating voltage, for example, could be 1.8 up to 2.2 volts, and what I've aimed for here is just a center point and say, okay, I'm going to drive it at 2 volts, and I'm going to and I know that the LED draws 20 milliamps typically. Now if I have 12 volts, what I've got to do here is I have to reduce the voltage which is being applied to the LED by 10 volts. And the way in which I do this is I can then use Ohm's law. And you can see on the right hand side here that we have 3 different formulas which we can then use to calculate the required resistance, and all that we need to know are 2 other things, and it doesn't matter what these 2 other things are. So in this case I know that I have 12 volts and I need to drop 10 volts, and I know that the current flowing in the electrical circuit is 20 milliamps. If I know the voltage that I need to drop and I know the current, then I can calculate by using the respective formula. So in this case R is the resistance, equals the required voltage that I need to drop, divide the current which is flowing in the circuit, i.e. 20 milliamps, and then by doing the calculation I then arrive at the required resistance value of 500 ohms, and that's what you see here. So at 20 milliamps, if I measure across the 500 ohm resistor with my multimeter, I will read 10 volts, and then that ensures then that 2 volts then are applied to the LED, and the LED will then illuminate. But if, for example, I only knew the electrical resistance value, but I didn't, for example, know 10 volts, or I didn't measure that, and it was 20 milliamps, you can see here that I could then calculate it by volts equals current times by the resistance. So 20 milliamps times by 500 ohms will give me 10 volts. And then equally so, if I wanted to calculate the current flowing in the circuit here, it's straightforward because we know the voltage, we know the resistance, and then I can then use that then to calculate how much current is then flowing through the resistor. So you can see with Ohm's law it's very easy to use the necessary should we say equation or calculation then to identify what is the volts, the current and the resistance, either being to be measured within the circuit or required within the circuit, and also the resistance which may be required then to decrease the potential difference or the EMF, which in itself then reduces the drive force then within the circuit. And we do this extensively. So any piece of electronic equipment, the designer has sat down and they have then designed the circuit, and by putting in the appropriate resistor values, and remember this resistor value can be a resistor, it can be a variable resistor, it could be a trimmer, but also as well you will have a required voltage, for example, that needs to be applied to a transistor to turn it on, or whatever is the electronic component, and the specification or data sheet will deem exactly what current is required. It could be in microamps, it could be in milliamps, it could be in amps. But the designer is able then to use Ohm's law then to calculate that. Now whenever you get any form of electrical resistance within a circuit, and even a piece of copper wire or maybe a gold plated contact has resistance. Now it might well be milliohms, very very small, but if you pass an electrical current through it, then you will get a voltage drop. And as soon as you are passing electrical current through a resistive circuit, no matter what it is, then heat will be generated. So if you think about your domestic appliances at home, you may have an appliance and you have a 13 amp outlet socket, say within your home, and maybe you have something which takes considerable amount of current. It could be, say, maybe a washing machine. You know that the electrical wiring in that circuit will have a larger diameter because of the heat that will then be generated when the appliance takes, for example, 230 volts and maybe 10 amps. A lighting circuit within your home may be rated at 5 amps because the amount of electrical current that is drawn would be less for a lighting circuit than it would then maybe for a ring main circuit within a house. So just before we sort of step away from this, there's one other important thing as well, because it really comes back to that statement where we talk about a resistor limits the amount of electrical current in a circuit. So what I'm going to give you here is a typical example. If you had an electrical circuit where the EMF, or the potential difference, the drive voltage, was, for example, 24 volts, and you had a circuit that drew 20 milliamps, if you put a 250 ohm resistor in that circuit, then as the current flows through the resistor, you would have a voltage drop of 5 volts across the resistor. If you then added another resistor in series with the previous resistor, so now the total circuit resistance now has increased to 500 ohms, the current would still be the same through the two resistors. But what you would now see is that you would have 5 volts across the first resistor, another 5 volts would then be dropped across the next resistor, and then I can then add in 2 more resistors. So now the total resistance in that circuit is 1000 ohms. The current flow is exactly the same because it's a series circuit, but now you have a 5 volt drop using Ohm's law across each one of the resistors. And then if I then added in another resistor, so now this would take you to 5 resistors within the circuit, the current would then flow through the 5th resistor at 20 milliamps, but the drive voltage now will have fallen, so it will no longer be possible to drop the full 5 volts across the circuit. So what would happen then is it would drop the remaining 4 volts across that last resistor, and now there is no longer a potential difference. So the current flow stops. And that's how the best way, or how I would ask you to then to look at that, okay? And we see this. If a resistor goes open circuit, then there can be no longer any current flow because there is no longer a potential difference. And then when I spoke about the heat that is then generated, we use a basic calculation. I've given an example here where you can calculate what would be the required wattage for the resistor. How much heat must the resistor dissipate? So here I'm showing that W equals wattage equals the current times by the voltage. So it's a 20 milliamps that is flowing through the circuit. I have a volt drop across the resistor of 10 volts. So that equals 200 milliwatts. So that resistor value can be 200 milliwatts or higher. And a nominal quarter watt resistor, 250 milliwatt resistor, would be adequate for this type of circuit. So a little bit complicated. I appreciate it. I don't want to get too deep into some of these tutorials, but and I do understand as well that often you'll undertake repair work without sort of spending years studying electronic theory. But if you understand Ohm's law, it does help you tremendously in your fault finding and also the way in which you would then approach fault finding. And if you're able then to build small electronic circuits, then it's even more beneficial there. So a little bit complicated, but glad you stuck with that. Hopefully you learned quite a bit there. Okay, right, let's move on. So what I'm showing in the next sort of overview here are really the broad range of variable resistors and trimmers that are used in audio amplifiers. And there are literally thousands of different types. So when you look at the top part, what I'm showing here are the different types of trimmers, right? And electronic manufacturers will use different types of trimmers depending on the application. But the resistance values, like the fixed resistors, will be linked to a particular series. But these trimmers, these variable resistors, can be both single turn but also multi-turn. So when I talk about multi-turn, what I'm referring to here are, for example, a potentiometer or a trimmer where you can rotate up to a maximum of 10 turns, and we use these commonly in biasing circuits. So a good example could be like a Cambridge 540 series Azure amplifier, and when you look there is a 10 turn trimmer and that enables you then to more accurately adjust as you rotate the potentiometer there, or the trimmer, to get a much more precise adjustment of the bias. Equally so, these potentiometers can also be what we call single turn, so a single rotation, but that doesn't mean it's 360 degrees. It isn't. Commonly it's about 160 degree rotation. And when they design these electronic circuits where you use the trimmers, really in terms of design, they tend to aim around midpoint. And the reason why that's important is I don't want to see an electronic circuit where you're on the extreme edge of the trimmer, either left or right of that. So it's its minimum resistance or its maximum resistance. So if you're repairing maybe an amplifier and a bias trimmer needs to be replaced, if you then repair it and you replace the trimmer, if you're really at the extreme ends of the adjustment to set the bias, that will tell you that there's something else going on within that circuit that you need to look at and then rectify. And then normally when you look at the service manuals, they will say, for example, set the trimmer to minimum value and then bring it up slowly, or they may say set it to approximate midpoint and then you can then make the adjustment. And we'll come back to this a little bit later on, but often in these tutorials I do like to repeat certain things for emphasis because they are important. So if maybe you were cleaning one of these trimmers in an older amplifier during a repair or service, if you rotated it backwards and forwards to clean off the oxide, you would normally return it to about a midpoint, unless otherwise to do so within the service manual, but typically midpoint or to the last position there. Now, when you look at the trimmers, again, they can have different types of mounting, and they may also have, for example, the one on the right hand side just before the decade box, the top right corner. Often these snap into a holding device, which maybe you have a hole through the front panel of a piece of instrumentation, and then that multi-10 turn pot snaps into it, and then you would then lock it in place with a locking washer and then nut then. In the midsection, what I'm showing you here are potentiometers, and again a very, very broad range which are available. And probably one of the most difficult things to sort of source are these types of potentiometers. So if an amplifier maybe is 3 or 4 years old and you can source the correct potentiometer, maybe it's a volume potentiometer that failed from the manufacturer, great. But if you're working on older equipment and you have a potentiometer that fails, some of these potentiometers are generic. So they are standard potentiometers available from companies like Alps or Borns, and you can order them and no issue there. But a lot of these potentiometers, and you'll see this again, I'll refer back in the video, they can be specific to an audio manufacturer's design. So what they will do is they will design the circuit, they will look at the design of the fascia, the appearance of the amplifier, and then we'll say, okay, we need a particular potentiometer of this ohmic value, we need a particular shaft length, we need a particular terminal length, we need the knob which then fits onto the potentiometer, what type will that be? And that's when things get really difficult on older equipment. And there's also, again, and I'll refer back to this later, we think about these potentiometers here used for volume, bass control, etc. But on older amplifiers they had something which are called biaxial ones, right? So biaxial type ones means that they could have, for example, a secondary shaft where you connect the balance, and then the front part then is the main volume control, and trying to source those is extremely difficult. So for people who are doing repair work, or maybe you're trying to source one, my advice based on experience is just click on Google Images when you do it in the search bar, because it's far faster to look at the images that come up to try and decide which potentiometer you want to go purchase than just doing a standard search and really doesn't come up with very much then. And then beneath the potentiometers, what I'm showing you here are motorized potentiometers, and again very, very common. So this could be an older amplifier, or it may be a newer amplifier, for example Denon, and it could be maybe a Denon 540, 720E, whatever it may well be. So 520 or PMA 520 or PMA 720 series amplifier, and they would incorporate these motorized type potentiometers. Now, inside the motorized potentiometer, and you'll see this a bit later on when we sort of show the internals of a potentiometer, typically what you have here is on the backs you will have a motor, and then the motor is typically 5 volts, and then you have a motor control circuit, and then from the infrared control circuit it will drive the motor in forward or reverse, and then that mechanically rotates the potentiometer from the rear. There will be a gearbox, and then that gearbox then will rotate the potentiometer internally, and then you physically see that when you're looking at the amplifier, because the volume control goes up and then it then goes down then. Now, the design of these again is very, very broad, so it could be a different shaft length, it could be a D-type shaft, it could be a split knurl type shaft. The range is huge, so trying to source these is challenging at best. Okay, and for myself, because I've been doing this a long time, I have a broad range of potentiometers, but even now, many years on, I still get amplifiers that come into the workshop, and trying to source these potentiometers is not easy. And then underneath what I'm showing here, and again you find these on older pieces of audio amplifiers, and like graphic equalizers, are slide potentiometers. So here with the slide potentiometer, it's the same as a rotary type potentiometer. It has a resistive track, and then you are then just simply tapping off across the range of that resistance then to provide attenuation for the signal that's coming through. The other example I'm giving here, and I mentioned this before, are these high precision volume controls. Now there is still a requirement, and customers still in many ways prefer a manual adjustment of volume control and other controls. So you can have an electronic volume control, you could have an electronic potentiometer, okay, but customers still want to use an electromechanical device, because just that feel when you actually increase or decrease the volume. So what you see here is an example where it is a potentiometer, but what they're doing is they're switching in banks of resistors, and these are high precision resistors because these are what we call dual, so for the left and right channel, and the resistors have to be ultra high accurate then, so you don't get any difference in attenuation. And then these high precision volume controls are not cheap to source, but if you're paying for a high-end piece of audio equipment, that's terrific. You can afford to have that. And then what I'm also showing here is a decade box, and you might think, well, I'm not too sure how that all fits in. Well, if you think, say, probably Audio Lab 8000 series, some of those amplifiers, they don't have preset trimmers in there to adjust the bias. And what they'll refer to is fitting biaxial type resistors, so a fixed value resistor, into the bias circuit then to set the bias. And you say, well, okay. Well, what we do in that case is we don't actually know what the resistance value should be until we've adjusted it, right? So what we do here is we can use a decade box, and what these decade boxes is, it's similar to the high precision volume control, where you have a bank of switches, and then what I can then do is by selecting the appropriate resistance value on there, so in this case I'm giving you the example of the range of this particular decade box, and the accuracy of this one is plus or minus 1% of the selected value. But there are other types of decade boxes manufactured like by companies called Time Electronics, where that accuracy there could be 0.1%, so ultra high accuracy. So what I'm able to do here is to connect what is fundamentally a variable resistor into a bias circuit, set it to a nominal value, typically the value which is already in there, but I need to make some slight adjustments. And then what I can then do is I can then increase or decrease the resistance value, and then at the same time I'm measuring very accurately across the emitter resistors commonly on the output stage, and then I can then adjust the resistance to the value required to set the appropriate bias, and then depower the amplifier, and then I can then make up the required resistance value using a couple of high precision fixed resistors then, and that's really what the decade box is being used for. Okay, and then in terms of operation, you may have already come across this if you're familiar with repairing amplifiers. There's a terminology which we refer to, and this is a dent type potentiometer. Alright, so what I mean here is that in the case of, say, the slide type potentiometer or the rotary action type potentiometer, as you operate it, if it's smooth, then that's exactly what it means, right? You don't feel any kind of resistance in terms of mechanical resistance. It's just smooth, fully open then to fully closed, 100% to naught. When you have a dent type, it depends on the function of the potentiometer. So it's not uncommon where maybe you have, say, a balance control, and that will be a center dent. So as you slide the slider up, it clicks into position at the center point, and then you can push beyond that. And the same with the rotary type, it goes to a mid position and you feel that center dent. And you might find that with a balance potentiometer, a treble, or bass. If you look at the volume control, if you think about power audio amplifiers, it's very, very common then to find a 41 dent type potentiometer. So as you adjust channel A, channel B, you can feel that indentation as you rotate. But you may also find the 41 dent type potentiometers in conventional home audio type electronic equipment as well. Okay. Alright, so let's move on now. So let me just talk to you about the different types of rotary potentiometers. Now, one of the most common type that you come across are type 12 and then also type 16 potentiometers. Type 16 are very, very common. And what I'm showing you here, and again, what I would say is pay no attention to these soldering pins in terms of lead length. You know, these are common, standard type 16, but those lead lengths there, or pins, could be much longer than that. Like I'm thinking about, say, a Cambridge, let's say A5 or A1, those lead lengths are going to be much longer, right? And then the same also then with the shaft length as well. You know, that could be 10 millimeters, it could be 15, it could be 25, all right? You don't know. It depends on the type that you have there. And then remember that the potentiometer shaft, you need to put some form of adjustment knob on there, and you have to select that depending on the shaft type. So when I'm looking here at the first one, what I'm showing you is a split type, and then it's a knurled shaft, and then this is the first time that we refer to this. We refer to it as a dual potentiometer or dual gang potentiometer. And switches are often where you have multiple wafers of the switch, so you need to have different inputs. Then we refer that then as a gang. So it could be a double gang pot, it could be, and again we talk about double gang pots being the most common, but that's not true. You know, you could have single, or on some of the older amplifiers they could have up to maybe 6 different gangs, each one of those then for each part of the circuit. But dual, very common. So when I say dual, I'm meaning that it has two wafers. Okay, so this could be for the left and then the right channel. Okay, and that's where we get this double gang from. And then in the center, you can see here that we're referring to this then as a D shaft. So this is a D shaft type potentiometer, and again the knob that then connects to that, you know, you need to source then to get the correct one. Probably the most difficult to source are these biaxial type. These are really difficult, I'll tell you. And again, they can be single and they may incorporate a switch as we're showing here, or it could be a dual type. And if it's a dual type, you know, that inner part of the axle, that could be for the balance control, and then for the one which is protruding out, you know, the inner one, then that could then be for the main volume control. And very, very difficult, you know. So again, you need to click on there and go look at Google Images to try and source some of these. Now you do have a workaround, and again providing some insight. if maybe you can only source a split knurled shaft type, and you say, well, actually I'm trying to replace a D type shaft, but I can't source that one. What you can do is you can cut off the side of one part of that shaft, right? So you're not going to go down the center section because it has to be the same thickness as the D shaft, but then you can cut it off so you have maybe 2 or 3 millimeters remaining of that shaft on whichever side. You've got to make sure it's aligned to mimic what you have on the D shaft, and then it's very easy then to just put in a slither of plastic and then put the volume or the balance knob onto there, and it will give you a very, very secure fit, and then it will work perfectly okay. But it's easier to get a workaround with the knurled split type than it is, you know, trying to get maybe a volume knob which originally fitted the split type and try and get that onto the D type. You know, that's very, very difficult then. And then I mentioned to you earlier, in terms of mounting, you know, they could be solder through like the ones that you see here, but maybe not. They could have lugs on them where you connect onto them, and remember that these could be mounted on the tone control board of the amplifier, and they may go through the fascia and then held in place then with a washer, as you show here on the D type, and then a locking nut that goes on the front then, and then the same also for the other examples that you see on here. Just be aware as well, whenever you get a locking nut onto a potentiometer, then where it's soldered onto board, that is always a stress point. So it's not uncommon, and we can maybe mention this when we get to the common types of faults, that you could see a crack on the wafer where maybe it's received, you know, a bump, maybe in transit, or maybe, you know, the amplifier was dropped, and then it just cracks through the resistive tracks, and then you look at it and you can see it from the back. But again, we can sort of talk about that a little bit later. And then when I talk about OEMs, I'm talking about original equipment manufacturers, and this is where audio amplifier companies go out and then will ask for a specific design of potentiometer to be made to their specification. And you know, it's not uncommon sometimes that you have to take a generic potentiometer and then try and do a workaround, maybe extend the lead lengths here to get it then to fit onto an older type amplifier. The next part of the video, what I'm taking here, is an example of a circuit. So this is a Cambridge Azure 340A Special Edition, and what I'm showing here is the schematic which shows the volume and tone circuits. Now when you have a selection called tone defeat or direct, and you select that from the front of the amplifier, all of that means then is that the treble, bass, and then commonly the balance controls will be no longer in operation, and then the volume then will be the main adjustment, or in some cases just simply the bass and treble controls are switched out, and you can still operate balance and then volume here. So I'm just showing you what it looks like, and you can see here that the resistors are shown, you know, as the oblong type. All right, so it's not the zigzag like for the older electrical type drawings, and then you can see the adjustment then which would then be made. So you have here two channels, right and left channel, and then you can see that it's connected then in circuit, and then depending on whatever the operator wants to do, as they rotate the potentiometer from its midpoint selection, left or right, then they can then increase the amount of treble within the audio or decrease it, and then also the same case then for the bass. And then what we're doing there is we just have different types of filters, and then we're also showing U2A and U2B. That's a single operational amplifier then, and then in turn then that goes across to the motorized volume control potentiometer, and again it's a dual gang type with a gearbox on the rear and then the motor, and the nominal value here is 20,000 ohms, and then on the other one you've got the, let me just check on that one, yeah, so it's 20k ohms. So for the treble control it's 20k ohms, and then also then for the bass control you have 20k ohms, yeah, for both. So 20k ohms for your bass and treble, and then 20 k ohms then for the volume control. But there is something which we call taper, and I'll come back to that in a little while. As I said earlier, you can then just switch out the tone circuits if you wish. So a good example here. Now, when we talk about tapers within an audio amplifier, it's very, very important to understand what we're referring to. But just because a potentiometer looks similar to another potentiometer, it may not be the potentiometer that you need, and you need to look for a different type. Okay, so let's give you some insight here. So in the middle of the video, what I'm showing you here is a potentiometer. Okay, so this is just, you know, what it would look like. Okay, so what you have are 3 pins, and then you have a resistive track, and then the center pin in this case, which is 2, is mechanically connected then to what we term as the wiper. And then what the wiper does is, because this is a rotary type, as I rotate the potentiometer backwards and forwards, then the wiper will then move across the resistive track. And by doing that, what I'm able to do, of course, is tap off a resistance value. So if we think about a volume control being an attenuator, as I increase or decrease, I will attenuate the signal, I will reduce it, or I will increase it by decreasing the amount of attenuation. Okay. Now, with the types of taper, when you have a look at a potentiometer, normally there will be some information written onto it. So I'm showing an example here on the left hand side next to the diagram which shows the connection pins and then the resistive taper diagram. It says B10K, and what B means is it means that it is a linear taper. Okay, and that means that if I rotate this potentiometer as an example to its midpoint, then if I measure between one of the outer pins and the center pin, I would read an ohmic value of approximately 5,000 ohms. Equally so, if I went from the center then to the other one, the right hand one as shown in the video, then it would read 5,000 ohms. So it's linear. Okay. Now typically B taper are used for bass and treble controls, but not in all cases. If you come across very old amplifiers, you may find a B taper is used for the volume, and equally so, and I'll come to that in a moment, there is a different type of taper which are normally used for balance controls, but not in all cases. And this is the importance here, that you have to go look at the variable or the resistance value and taper type written on the potentiometer. All right, because it's not, this is always the case. Sometimes it's not always the case. All right, so when I talk about B, and I can see it here, I'm talking about a potentiometer which is linear. Okay, now more commonly when we refer to a volume control potentiometer, it will normally have a letter A, and A stands for audio taper. And you say, well, you know, what's that kind of referring to? If you did a Google search, you would tend to come back with something called logarithmic. Okay, so what that means is that the resistance that starts off relatively low and then increases, or it could be the inverse of that. So if I'm thinking about a volume controller on an audio amplifier, as you rotate it, if it was an audio taper, then of course the volume increase or decrease would no longer be linear. So if I set it to 25%, for example, it wouldn't be 25% of the output power of the amplifier, right? It would be different because it's now following a logarithmic or an audio taper. So initially, as I'm rotating it, it's making small changes to the volume level until you reach about 50%, and then when you go past that, it goes up quite quickly. And that is what we term as a logarithmic type or an audio taper type adjustment. And most volume controls either have a standard audio taper or a reverse taper, i.e. if you looked at the resistance taper versus rotation, in this case it would just be inverse to what would be a normal audio taper, a non-reverse. The next type is M&N or MN taper, and you may find this in many amplifiers. So when you get to say the balance control potentiometer and you remove it and maybe you have to replace it, you look at it and it says, for example, MN 20K, and you think, well, it's not an audio taper and it's not a linear taper, so what's this? Well, we refer to this as a blend balance type. And if you think about the balance controls which were used, many years ago, because you had a lot of tolerances in these different resistors, and even with these volume potentiometers, you could have a tolerance of say 20%. The left and right channels were not exactly the same. The same with the speakers. They weren't manufactured to a level of precision like today. So often, what the balance control was being used for was to compensate for differences in either channel. And you know yourself with your own hearing, right? You may say, well, my right ear, is a lot better maybe than my left, and that's just normal, right? Nothing's exactly the same. So here with the blend type, as you rotate it, you're able then to increase more the left or decrease more the right, depending on what you want to do. And again, for guitar type amplifiers, it would not be uncommon to see an MM taper, say on a bass amplifier, and then they would then refer that then to a blend balance type. But as always, that's not always the case. All right, so you may well find an MM taper in some amplifiers, and you look down and say, well, that's the bass and that's the treble control. So why is it MN? That's just what the designer has specified, and that's what's then been installed. And then the other one, and this really does catch people out, right? So if you're undertaking any type of repair work, probably make a note of this. This is where the potentiometer has a loudness taper, and you will have seen these types of potentiometers if you've repaired amplifiers before. So commonly, you may have a single gang and you have the 3 connections, or as shown in the video, you have a double or dual gang and you have 6. And then you look at this one on the bottom right and you think, well, hang on a minute, that's got 8. So what's going on there? The reason why it's got 8 is that the 4th connection now is the loudness taper. So now you have a resistance tap-off point from the main resistive track. And a lot of amplifiers have a loudness switch on the front. And I'm thinking, for example, maybe a Denon amplifier or even a NAD amplifier, some of the earlier ones, and you get the volume potentiometer out and it's like 20K, and then you look and think, well, there's a 4th connection here, so that's fine. I'll just put a standard one in, which has got 3 leads on or 6 leads. But what you've done then is you removed the operation then for the loudness function. So normally the loudness function is selected by means of a push button on the front of the amplifier. So when you press it and it says loudness, what it's doing is it connects in that connection there, so it's tapping off a part of the signal, which then increases the loudness then of the amplifier. So this is what we call a loudness taper. All right, so just for clarity there, for your own insight. And then the next part, and really the final part, I don't think we can cover too much more on the physics and what the layout is of different types of potentiometers. What I'm going to talk about here are the typical types of faults that you may well encounter and how to rectify them. And some of these, are very, very useful because they can get you out of a hole, right? So when you look at the video, what I'm showing at the top left-hand side is I'm referring to single gang potentiometers that you find in power amplifiers, okay? So these are the rack-mounted audio power amplifiers which are used in studio work or maybe useful venues. What you'll find there is that these could be, again, say A10K, so it's a single gang device, but what you have is you have a rubber cover over them, and then that helps to prevent dirt going directly then onto the carbon track in this case, because it would be a carbon type, and then creating the telltale symptom of noise. And we're very familiar with this, where you adjust the control and you get this scratchy sound or maybe a rustling sound, and then you get this intermittent loss of audio, and then that's very, very common. So what these rubber covers do is help to try and mitigate that. And remember that in most audio power amplifiers you will have multiple fans, and you'll have some degree of cooling, and then air gets pulled in that contains dust, and then it gets driven through the amplifier. It's very, very common that you open them up and you have a thick layer of dust, and of course you need then to also clean the volume control potentiometers. But remember, common in these would also be a 41 dent type. The next one on the right then to these potentiometers are the slide type, and these again are very, very common on older pieces of equipment. And in terms of cleaning them, the same with any potentiometer, you should always use a high quality switch cleaner or contact cleaner. And I'm giving you an example here of the K-Lab Ink Deoxit series, and they make a broad range of different types of cleaners and also grease, which I use extensively within the workshop. So in the case of the slide type potentiometer, again you would move it, you hear this scratchy sound, and then you can then apply the deoxit directly into there. Just wait maybe 10 or 15 seconds, and then you just have to work it backwards and forwards multiple times. Same also with the rotary type, rotate backwards and forwards. And normally you're going to do this without any speakers connected, but again inside, if it has a headphone jack on it, not the power amps but the hi-fi amps, I just plug in the headphones, stick them on my head of course, and then I can then listen for noise. And what you may well find is it tends to be like at the extreme ends, so it could be the beginning minimum setting or the max setting, where maybe the volume control hasn't been used extensively, particularly at the high end, or you may just find like a dead spot. So don't just spray the deoxit in once. You might need multiple times to leave it a few minutes, but in most cases you should be able to recover the potentiometer so you no longer have any noise. But not in all cases. Sometimes you do have to replace it if it's physically damaged. The next one is these preset trimmers. Now the preset trimmers, and on the previous audio tutorial that I went through, I talked about silent killers, which seems a little bit of an extreme language, but these things again are typically used for adjusting DC offset and most importantly the bias within audio amplifiers. And when they fail, you have an output stage failure, these resistors just burn out, and there may be no physical appearance, anything untoward, but you need to remove them and then to measure them and ensure that they're not open circuit, right? If they're not open circuit and all is good, what you can do is you can again spray in deoxit, and then with the amplifier switched off, don't do it with it switched on because obviously this is a bias trimmer, you can rotate it backwards and forwards a number of times, leave it for a few minutes, repeat again, return it back to the same position that it was in before, and then you can then do the final adjustment then for the trimmer. Now underneath there, what I'm showing here is the insides of a type 16 potentiometer. All right, so what I've done is I've just removed the real wafer, and you can see it here. So what it shows is the three terminals, and that's the in the middle there, and then you see the resistive carbon track. Okay, so that's one of the gangs, so that would be a dual gang pot in this case, so that's the second gang. And then to the right of that, that is what we call the wiper. All right, so it's connected to a plastic, which then connects then to the metal shaft. As that comes through the front of the potentiometer, then connects the first gang, and then that then goes onto the wiper then for the rear gang. Okay, so typical types of faults that can happen here is you could have mechanical damage to the wiper. So maybe the leads have broken off, and you look from the back and you can see a light brown line, and then you realize that it's gone through all three of those connections. Or you may have something which is again very, very common. Maybe the volume control potentiometer has been rotated beyond its end stop points, and this isn't uncommon if you maybe have small children in the house and they've just gone up, rotated it, forced it past its end point. So what I'm showing here is the inside of that, right? So what you have is a metal tab, and then the actual end stop is on the plastic material on the first gang. And what happens is the metal tab just cuts through the plastic, but if you just get a pair of long nose pliers in there and just bend it slightly 45 degrees, you will then fix that end stop, because then when the plastic stop hits it, it doesn't cut through it as it did when it was damaged. It now hits the flat of it and it will work perfectly fine, you know, and then that avoids having to go source maybe a potentiometer that you can't go get. In some cases I've replaced the secondary gang, as you can see here, right, from a donor potentiometer, and that's worked very, very effectively. But because the shaft is mechanically fitted directly then to the first gang wiper, it's machine fitted, so you can't get that off there to make the repair. So in that case, if the first gang was damaged, then I have to replace the complete potentiometer. And then in terms of cleaning these potentiometers, I'm just showing you which is common. Alright, so here with a type 16, you would have two holes, left and right, and then what I'm able to do then is to spray the switch cleaner directly inside, leave it for a while, and then rotate it backwards and forwards, as we said before, then to clean the oxidization off the resistive track. Or, and again you may find this on other amplifiers, there are no access holes. You know, it's using maybe a type 14 potentiometer and you can't get in. But what you can see is underneath I can see access then to the wafers within the potentiometer. So what I have to do here is, of course, remove the potentiometer from the tone board, and then I can then take it out. I can spray directly into there and then again work it backwards and forwards. Now when you're doing fault finding, you know, because this is a resistor, a variable resistor, it's a simple case of using your multimeter on resistance. And what you need to be doing there is, you know, from the ohmic value 20k, you will have a nominal 20,000 ohms if I measure from the two outer points, not with reference to the wiper for the potentiometer. But remember that all these potentiometers have a tolerance, right? So I'm not going to measure and expect to see 20.0 k ohms. It may be 19.8 k ohms. But as long as the two gangs are nominally correct, then that would be fine. But you may well measure one of the gangs and maybe you don't get any resistance values between the wiper and maybe one of the other connections. So that would tell you that, you know, it was open circuit at that point. Or you may well measure between the two outer points, not the wiper, and again you could measure that it's open circuit. And this is not uncommon for volume controls. So you feed the audio signal in, it gets processed, and then it reaches the volume control, and then you measure it and you say, okay, I've got audio going into the two gangs, the left and right channel, into the dual gang potentiometer, but now when I'm measuring on the wiper, I've only got output from one of the gangs. So that means that the potentiometer then has failed. Equally so, and this again is not uncommon, a customer may say, well, I've actually got a difference in volume, okay, and it may not have anything to do with the processing circuit. You know, you don't have some issue there when you put, for example, your oscilloscope onto there. The input signal for the left and right channel is the same amplitude going in, but then when it's then coming out, and this is a dual pot, so it doesn't have two shafts, it's a single one, you get a difference. Now it may purely be that the track, it's just dirty, so you just need to clean it. But if that resistance has changed over time, and again, like all resistors, they can, then the ohmic value then is no longer within tolerance to the other gang as well, and you'll probably need to replace it then. Okay. Now on the top, there's a couple of things here, and I tend to refer to these as hacks, all right, and they're kind of useful. So the first hack that I'm going to talk about is the one at the right hand side, which is this nylon fishing line. and this is going to save you a huge amount of time, trust me. So if you maybe have a balance control, treble or bass, the shafts of these potentiometers are quite short. Okay, so if you're cleaning them, originally you would have lubricating grease, which is around the around the potentiometer shaft. But remember, those controls really haven't been used to the same extent or rotated to the same extent as the volume controls, right? Because you tend to set your position, you leave it there, so you can then clean away and all's good, and they're moving nice and freely. But what you don't feel is any looseness between the collar and the shaft itself. All good. But you get to a volume control and maybe it's a little bit difficult to rotate, and then you then go in there and you clean it, and then what you find is that some of the original lubricating grease, which had dried hard, then starts to dissolve, and then you refit it, and then you put the volume knob on and it feels loose, not terribly loose, but it doesn't feel that great when the customer's rotating it. It feels a little bit kind of sloppy, and you think, I've got to go out now and I've got to go source now a replacement potentiometer, and maybe it's one of these which is like a unicorn trying to find one. So what I do here is you can use nylon fishing line, and what you can do is you can literally pull the motor shaft forward around from the collar, and then you can then just tie some fishing line and just rotate it or wrap it around just a couple of times and then tie it off. And then what that does is it fills the gap then between the collar and then the motor shaft or the potentiometer shaft. Okay, and then it's just a simple case of just putting some lubricating grease around there, and it's like fitting a nylon slip washer. And then when you put the knob back on, absolutely perfect. There's going to be no sort of wobbling around or anything like that, and you get that nice sharp feel on the volume control, and it works really, really well. And I've used that for many years, and it's excellent. So again, you may have your own amplifier and you've seen that you can use the fixing line then to do it. And then the other one that I'm showing you here is this conductive paint. So again, when you think back, maybe you had a rear heated window in a car, sometimes that resistive track got damaged. So what you could then use is some conductive paint then to repair that. So what I'm talking about here is I'm not using conductive paint to provide a sort of mechanical high stress repair, right? Because that's not going to work. What I'm referring to here is that when you have these contacts, they are sort of riveted directly onto the resistive track, and sometimes they can just become a little bit loose, right? So nothing of any significance, but it's not taking any sort of high level of stress. So what I can then do is I can just repair that. So this isn't the resistive part of the track, this is the non-resistive part, because it's conductive paint, should be lowest possible resistance, and then I can then paint this on, so it's quite thick, and then that will then act as a very good repair in those types of cases then. Okay, now, and I see this a lot, right? So you see this on forums, and then you also see this as well on emails that I get directly from a channel, right? And this is about WD-40. Okay, now WD-40 is neither a lubricant and it is neither a switch cleaner. Okay, let's rephrase that, right? It is not a potentiometer cleaner, okay, and it is not a lubricant, right? And you might say, oh, hang on a minute, it is a lubricant. Well, actually it's not, right? So where the term WD comes from is it's water dispersal. So it's a water dispersal product, okay? Now, when I talk about lubricant, right, it will give you short-term lubrication on maybe a hinge or something like that, but its fundamental purpose is to displace water, and then you can also use it as a cleaning product, right? So it's not unusual, for example, to use WD-40 to clean metal parts, which could be maybe rusty or they're stock. The absolute thing you never ever want to do is use the blue can WD-40 and spray it into a volume control bass treble potentiometer. because if it's carbon based, what will happen is it will start to dissolve the hydrocarbon that's made out of. So you spray it in there, you work it around, you say, oh, it's going to clean it, and then after a few minutes it's like, what just happened? Well, what just happened was the carbon track of the potentiometer just got, damaged because of the WD-40, right? Now, the same company will make switch cleaner, right? And that is a different product to the blue can WD-40, right? So excuse me, so in that case, if that's a high quality switch cleaner, great, you can use that, but don't spray the WD-40, right? If you're using it on switches, again, use specialized contact cleaner, but remember that it's not a long-term lubricant, right? So when I work, say, on encoders, or maybe I use this hack here for the nylon fishing line to fix the issue with a wobbly motor shaft or potentiometer shaft. What I'm using here is one of the products that you see displayed here within the Deoxit series. Alright, so if I need to lubricate something, I want to use a proper lubricant because it's designed to provide longevity, and that's what I need to do then. But I do appreciate WD-40 tends to be lying around the household, and it's used for pretty much everything and anything then. Okay, so really coming to the end of this tutorial. So hopefully you've learned a great deal. You've got a lot of insight, and always, as I say, if you have any questions, you can at any time just email directly to audio amplifier servicing at aol.com. I'm happy then to come back and answer any questions you may well have, or equally so you can just leave a message with the respective videos, and no problem, I'll pick those up regular basis, and then I'll then just come back to you. Alright, so as always, thank you very, very much for stopping by, and until the next time, thank you and goodbye.